control panel. And we're going to wait until the very end of the webinar. We're going to have 2 presentations today. And when we get to the end of it, we will answer those questions. So be thinking of them as we move along this afternoon. So with that, I would like to introduce, well, I should introduce myself first. I'm Laura McKay with the Virginia Coastal Zone Management Program and a member of the Mid-Atlantic Regional Council on the Ocean, which is sponsoring this webinar series on corals, deep sea corals and canyons. I'd like to introduce Kim Cole. She is the program manager for Delaware CZM and I think NEARS too. Hi, Kim. And Kim is going to be our new MARCO chair next week, July 1st. She begins in that role, so we've already roped her into working on that as MARCO chair today. So welcome, Kim, and thanks for being with us.
Great, thanks, Laura. I'm coming through.
Yes.
Great, thank you. So good afternoon and happy Ocean Month. On behalf of the Mid-Atlantic Regional Council on the Ocean, also known as MARCO, I'd like to welcome you to our webinar, Climate Change Impacts on Deep Sea Corals. MARCO is the regional ocean partnership for the Mid-Atlantic, established in 2009 by the governors of New York, New Jersey, Delaware, Maryland, and Virginia. MARCO is an interstate collaboration to address shared regional priorities and provide a collective voice on important ocean issues that transcend political and geographic borders. As Laura mentioned, beginning this July, just next week, I'll have the honor of serving as chair of MARCO for the next 2 years. And I'm very pleased to be able to introduce today's webinar. MARCO focuses on 4 shared regional priorities in the Mid-Atlantic: climate change adaptation, water quality, marine habitats, and renewable energy. Our Corals and Canyons webinar series aligns with 2 of these priorities: climate change and its possible effects on deep sea coral habitat. Today's was planned in response to feedback that we received during previous webinars. Attendees were interested in learning more about how climate change might affect deep sea coral, a unique and important marine habitat. Please visit our website to view any of our previous webinars and to learn more about MARCO's work. I'm also pleased to welcome our speakers, and I thank them for joining us today to present their work on impacts of climate change on ocean environments. Dr. Carol Ann Clayson is the Associate Director of Research Strategies at Woods Hole Oceanographic Institute, and Mr. Ryan Gasparo, a Presidential Fellow and Doctoral Candidate at Temple University. I would also like to thank the Gordon and Betty Moore Foundation, whose support allows MARCO to, among many other things, highlight our region's ocean ecosystems and the important work that's being done to better understand these areas. And finally, I'd like to thank everyone in attendance for joining us today. I hope you're as excited as I am to learn more about the role of the ocean in Earth's complex climate system and how the unique deep sea coral habitat might be impacted by changing climate conditions. So I'm going to pass the mic back to Laura McKay now, who will get us started. Thanks.
Thanks so much, Kim, and we're so excited to have you as our next chair and appreciate all your efforts. I know it's going to be a great couple of years, and our thanks to New York, who has been our chair for the past 2 years. Okay, so we're going to get started now, and I wanted to provide a little more introduction to Dr. Carol Ann Clayson. We're so happy to have her. She is, again, the Director of Research for Research Strategy at the Woods Hole Oceanographic Institute and a former Director of the Ocean and Climate Change Institute. And her projects are aimed at understanding the physical processes occurring at the boundary of the ocean and the atmosphere, and how data, understanding, and modeling improvements can translate into better climate and weather forecasts. And her current research includes ocean mixing processes and how air-sea interactions affect the climate and ocean impacts on the global water cycle. Her research has been supported by the Navy, NSF, NOAA, and NASA, and she received an NSF Career Award and the Office of Naval Research Young Investigator Award. She has a bachelor's in physics from Brigham Young University and a master's and doctorate in atmospheric engineering, atmospheric and ocean sciences from the University of Colorado. So thank you so much for joining us today, Carol Ann, and hopefully we can have you share your screen and pull up your presentation. Great. We see you, and your presentation is there, but small.
All right, let me.
Can you make it larger?
It should be larger now. Okay.
Great. Thank
Great.
you, Carol Ann.
Thank you so much for inviting me here to here to your webinar, wherever you are virtually. And I'm just going to give a little bit of a sort of a global context of changes in the ocean and the impact that the atmosphere has on those changes, and then turn it over to Ryan to really focus in on the deep sea coral component of this. When I think about the climate and the role of the ocean and sort of the general Earth's climate, I like to talk about the atmospheric engine. So if we start with that, first of all, we have the sun, which I think of as the refinery of the system. And then the sun's energy comes through the atmosphere, which is really the pipeline, and it's a little bit of a leaky pipeline. So some of that energy is lost. But some of it comes down and it heats the upper part of the ocean. And I'm going to talk a little bit more specifically about that heating of the upper part of the ocean. But for now, let's just say it heats the upper ocean, and the ocean then becomes the fuel tank for the atmosphere engine. The ocean exchanges moisture and heat with the atmosphere. And that moisture and heat contributes to the creation of warm, moist air, which really becomes then the fuel for the atmospheric engine. And that fuel then drives the engine itself, which is the wind, which moves that then warm, moist air around the globe. But it also exchanges momentum back again with the ocean and helps to create waves and currents. And so in that sense, then the wind becomes the brakes, or the ocean acts as the brakes on the momentum exchange and on the wind. So there are a lot of processes where this sort of this dual aspect of the atmosphere is driving, or the ocean is driving the atmosphere with heat and moisture, and is also acting as a brake to the energy in the atmospheric system. Think of this, for instance, during a hurricane, where the ocean is exchanging heat and moisture with the hurricane and thereby giving it fuel, but it's also acting to brake it as the wind blows across the ocean and that energy is lost to the ocean. And a very interesting area of research, of course, is how much energy and momentum and heat get exchanged during high wind events, so that we can understand better that fueling and that braking that are simultaneously happening. Of course, what this does is it transfers moisture and energy between the ocean and the atmosphere. And one of the things that results from this is the global water cycle. And you can see these numbers here. It's not very important exactly what the numbers are, but they are in 1,000 cubic kilometers per year. This is how land hydrologists like to talk about the global water cycle. And this is some work that was done with a group, and we were trying to make an estimate of all the components of the global water cycle. What I would like for you to note is that if you look over the ocean, those little arrows there, that's the ocean evaporation, and that number is almost 450. And again, 1,000 cubic kilometers per year, but 450. And if you look through the rest of the numbers in the system, none of the other numbers are that large. The ocean evaporation is the single largest component of the global water cycle. It really is the driver of this. And if you look at our estimates for uncertainty, that number is about 22. How large, that might not seem like a very big number, but if you look down at the river runoff is about 46. That is the global river runoff. If you took all the rivers across the globe and you added up all of the runoff for the entire year, that's about 46,000 cubic kilometers per year. And our uncertainty in the ocean evaporation is a full half of that total amount. So there's some work that needs to be done, and I'll do a little bit more about things that we're still learning about in a moment. So salinity is really the ocean imprint of the precipitation minus evaporation, which is what we call the freshwater flux on the ocean. And of course, salinity is another key component of the ocean that affects ocean life. So one of the things that we focus on. So here we have evaporation minus precipitation. So where it's red, it's very dry. The ocean is evaporating a lot, becoming saltier, and where it's blue, then the ocean is becoming fresher. And if you look down at the bottom right, that kind of lines up with where it's more saline and less saline in the ocean, roughly speaking. So really the salinity, the ocean salinity is really that ocean imprint of the global water cycle. The other thing that is happening, of course, with the heat is that the fuel in the tank is increasing. That's how we like to talk about it. And you can see from this series of curves where that extra energy, the additional energy that's being trapped by the Earth system, where that is being stored. And you can see that I like to show this to folks because basically all of the blue is the ocean. The brown is what the land is storing. The gray is what the ice is storing, and that little bit of purple down there is what our atmosphere is storing. So as you know, the ocean is storing about 93% of all the extra heat in the ocean, and these numbers are in zetajoules. So there's roughly, over about a 55-year period, the ocean took up about 240 zetajoules of heat energy. So just to put that number in context, if the lowest 10 kilometers of the atmosphere had absorbed that much energy, it would warm by about 36 degrees Celsius, almost 65 degrees Fahrenheit. And I like to say at this point that we probably wouldn't be having a conversation about whether it's warming, whether there is global warming occurring or not, if we'd warmed by 65 degrees. So it's great for us in a certain way that the ocean is taking up that heat, but of course the ocean then warms, and that impacts once again on ocean life. So the other thing is that because we're adding energy to the fuel tank, that sort of speeds up our whole water cycle. So we get more evaporation and we get more precipitation and more river runoff. We think that this will cause more extremes. So you'll have more extremes of flooding and drought across the globe. And we like to say that wet areas look like they will get wetter and dry areas will get drier. So basically a redistribution of precipitation from the mid-latitudes to the high and low latitudes. So this will have a great impact on land. And obviously the salinity variability in the ocean will be impacted as well. So in general, the ocean seems to be getting somewhat saltier. One thing that we talk about is that, again, we do see the imprint of E minus P, the freshwater flux on ocean salinity, but that trend, how great that trend is let's just say it's somewhat elusive. This is 9 different realizations of the change in salinity over the past few decades. And again, with the blue indicating fresher regions and the red saltier regions. And you can see, depending on which model you're looking at, which data set you're looking at, there are some differences in terms of the magnitude. If you look down, in fact, at the mid-Atlantic region, you can definitely see this is a region of much increasing salinity. So that's something, even almost all, but not all of the models have that. But it's just to the extent to which that occurs. So if we look at the other side of it, what's the global trend in ocean evaporation? Well, if we look at a bunch of satellite data sets, so all the different colors here on these lines are the changes from a mean of evaporation from 1980 through 2015. And the different colors are just different satellite products. And with the purple line being a set of 20th century climate model simulations, which you can see have very little variability. Some of the satellite products have an extreme amount of variability and some of them don't. And so we're still trying to disentangle some of these questions. And the reason that we worry about this is that if we want to make projections of how salinity is going to change in the future, we have to get right that connection between the ocean and the atmosphere to get the right amount of evaporation, the right amount of precipitation, so that we can have more confidence in our projections. Of course, the heat, moisture, and momentum are not the only things being transferred at the ocean surface. This is a little bit more inclusive of a statement here about what is going on in the upper part of the ocean and the lower part of the atmosphere. And we, in addition to moisture, heat, and momentum, we transfer carbon dioxide, aerosols from sea salt droplets that then make clouds, sulfate particles from DMS, and more. are being exchanged between the ocean and the atmosphere. And what we like to think of is that some of these are very small processes. I'm going to mention bubbles in the upper ocean, and they're happening right at the very surface, and yet they have a big impact. So if we look at what's happening with our oxygen levels in the ocean, which is of course a key thing, this really affects processes ranging from biogeochemistry to food security. This global map indicates a lot of coastal sites where anthropogenic nutrients have exacerbated or caused oxygen declines to less than 2 milligrams per liter, as well as ocean oxygen minimum zones at about 300 meters depth, which is where the blue shaded regions are. So the open ocean has lost an estimated 2% of its oxygen over the past 50 years. And this is a continuing factor, and this upwelling has intensified in severity over the last decade or two, and especially along the coast. And you can certainly see that along our eastern coast. So I'll just give you, I'm going to give you just a few little examples of current research and kind of where we are in trying to understand and predict how this oxygen variation is going to occur. So this is now a nice set of data that was taken in the Labrador Sea. The uppermost panel here is the wind speeds over that year time period. And then there's oxygen and carbon dioxide estimates. So in these, this is now the flux or the exchange of oxygen between the ocean and the atmosphere. And when that value is positive, the ocean is outgassing. And when it's negative, there's an influx of the oxygen to the ocean. Some amazing things that came out of this study is that, first of all, about 2/3 of all of the oxygen exchange in this region happened over 40 days in winter from these major storm events. So very small scale in terms of time and space events had a major impact on the oxygen uptake. But the other thing that they're looking at here is when they include bubbles into the model, the flux model, the exchange model that they have, they get a very different number. So if you don't include the bubble component of the bubble impact on the exchange, which no global models do, the results of this indicate we may be underestimating the oxygen and atmospheric potential oxygen uptake in regions where you have deep water formation by up to an order of magnitude. So again, very small process happening right at the very surface, those little bubbles. We're looking at something that could be an order of magnitude difference. And this is not something that's currently sitting in our global models. And you can see there's an impact as well on the carbon exchange between the ocean and the atmosphere of the bubbles too. So this storage of carbon by the ocean, as we know, is significant. The oceans are taking up about 25% of the excess carbon dioxide, which has impacts back on acidification. And Ryan will talk much more about the direct impacts of this on corals. We believe in the past the oceans took up a higher percentage of this. What's going to happen in the future? And you can see on the left here now is a panel of the change in the anthropogenic carbon now in the ocean. And this is at 400 meters. And then on the right is the change in carbon over the entire water column. And what you can see here is that, again, there's a great deal of increase in the amount of carbon within the ocean itself. And you can also see that the North Atlantic is kind of a hot spot for this carbon exchange and storage. So as I mentioned, we talked a little bit about the bubbles, and I'm going to come back now and finish with talking about that warming of the upper ocean. So again, to emphasize that what happens right near the surface really matters everywhere, because that's where the exchange of heat, moisture, momentum, carbon, oxygen, and other gases takes place. So if the winds kind of remain somewhat light, around 3 meters per second, this is just a simulation with depth and then for a number of days and the temperature. And what you see is every day the upper ocean warms up, and then it cools down a little bit at night and warms up again. And so you get a profile where you get temperature that's warmer near the surface than down below. All right, so there's actually something else that happens as well. So here you can see these are two profiles. This is the nighttime profile, and this is a daytime profile on the right. And you can see that warming in the upper part of the ocean during the daytime, which is not evident during the nighttime. And then right near the surface, this is a log profile. So just in the upper, less than a millimeter, there's also this cooling, we call it the cool skin effect. So we've got this little cooling here at the very top, and then a deeper warming down below. Now, why does this matter? Okay, this matters because this is a nice work that was just done by Andy Watson, who did an analysis of saying, okay, if I estimate the flux between the ocean and the atmosphere, and I use different depths of temperature, what does that give me? So if I just use the depth, which is common now for Argo data to be from ship intake data, and in fact, what has been used for SOCAD and for other estimates of carbon flux between the ocean and the atmosphere on a global scale, this is the flux that I get, okay, which is less than, there we go, if we use the value that's much closer to the surface, and during the day, you get a larger flux into the ocean. And then if you are even more careful and use the actual temperature at the surface of the ocean, you get even more flux into the ocean. And in fact, that difference is large enough that you can see a couple of things. So first of all, the blue dashed line here is just an old estimate of the carbon flux between the ocean and the atmosphere using a deeper temperature. The red dashed line is yet another older version of this. And this strong red line here is the estimate of what the flux should be over sort of this time period by looking at how much carbon changed in the ocean. So the others are trying to estimate looking at the winds and the amount of partial pressure of CO2 in the atmosphere and the ocean. So they're estimating how much is actually being exchanged. This solid line again this is how much is being exchanged based on how much it's actually changing in the ocean. And what you can see, over this time period is that both of the older estimates seriously underestimate that. This solid black line is now the estimate that is made using the actual temperature, the very topmost temperature of the ocean. So we're talking about processes that are happening over millimeters to a meter or two in the upper part of the ocean, and then impacting back on the total carbon, oxygen, and other heat in the ocean. So I'm just going to leave it with this and say that, as I mentioned, the temperature is increasing, which impacts back on the oxygen. Our salinity and carbon appear to be increasing elsewhere, but the amounts of this change are somewhat uncertain. And that's partly because our exchanges with the atmosphere, which cause these ocean changes, are even more uncertain. So we're somewhat uncertain in how much it's changing, and then these exchanges are even more uncertain in understanding and physics and chemistry that's happening. So however, the key part is that predicting changes in the ocean relies on accurately predicting these air-sea exchanges, and we really do need to be improving the physics and the biogeochemistry of these. And as you can see, the North Atlantic is really a hotspot for many of these changes. So I'm going to end here and turn it over to Ryan, who's going to now give you a nice discussion of the deep sea corals.
Thank you so much, Carol Ann. Wow. I'm encouraging people to put their questions in the question box. That was a great primer. Well, I think it was a little above primer on what's going on with those interactions there in sea surface. So thank you so much for that. And that really does set the stage for what Ryan Gasparo is going to talk with us next. And just to give you a little more background on Ryan, he is, as you can see on the slide, a PhD candidate at Temple University with interest in understanding how animal communities are structured within and across dynamic ecosystems, particularly the ones in the deep ocean. And that has led him to work in intertidal zones, fjord basins, hydrothermal vents, submarine canyons, cold hydrocarbon seeps, and cold water coral reefs. And his current research focuses on the latter three locations to predict seafloor biodiversity responses to climate at a range of scales. He's currently a presidential fellow in Temple University's Department of Biology, and he's working under Dr. Eric Cordes. And he has a master's in Earth and Ocean Sciences from the University of Victoria in British Columbia, and a bachelor's with honors from Arizona State University. So thanks so much, Ryan, for joining us, and we look forward to hearing how everything that Carol Ann just described is going to affect these beautiful deep sea corals. So if you can, do you want to turn your camera on, or you don't have to if you don't want to. There you are. Great. Thank you so much for coming today, Ryan. We sure appreciate it.
Thank you, Laura, for that introduction. And thank you, everyone, for attending. I'm really happy to be here today and talk about some of the work that I've been doing for the last couple of years. So I'll just start with a little outline of what I'm going to be talking about. I'm going to start with a really brief overview of corals in the deep ocean, their diversity, and the suite of threats that they're facing in the 21st century. Dr. Clayton did a really good job talking about warming and deoxygenation, so I'll give just a really brief overview of some of that. And then I'll go to what I've been working on for the last few years now, which is studying this coral you see in the background here, Lophelia pertusa, on the southeast U.S. margin. So that goes from Florida up to Virginia, so a little bit south of the Marco region, trying to build habitat suitability models that predict their distribution, the abundance or the cover of Lophelia on the seafloor, and using climate models to predict that there will potentially be climate refugia off the shore of the southeast U.S. And then I'm going to look north to some of the coral diversity in the mid-Atlantic. So a brief overview of cold water coral ecosystems. So cold water corals are a diverse group of cnidarians that live below 200 meters where sunlight is not available. Therefore, they don't get nutrition from symbiotic algae like their shallow water counterparts. They rely on sinking particles from the surface to survive. So because Lophelia is the main species that I work on, most of my talk today will focus on the stony corals. So these are the ones that build the reefs in the deep sea, and they're also solitary cup corals as well here. But there are also really diverse groups of soft corals in the deep ocean. So these are include precious corals, sea fans and sea pens, bamboo corals, and black corals like the one pictured here on the bottom. But for stony corals, there are 6 species in the deep sea that are significant ecosystem engineers, and they can form these ecosystems. Basically, their skeletons accrue over many generations. So this goes on for millennia, where the dead skeleton is left behind, and then the living skeleton builds on top of that. And over time, these carbonate mounds from the skeleton are formed. So they trap sediment within them, and then more skeleton piles on, and they can form these really dynamic ecosystems, isolated mounds on the seafloor, mound provinces that stretch for dozens to hundreds of kilometers, and it's some areas where these mounds coalesce into contiguous reefs, like a couple that I will show in the South US. But the non-stony coral groups are also really important in that they provide structural habitat for fish and invertebrates too. And just cold water corals in general provide a lot of ecosystem services that we rely on. So it includes nutrient cycling, so the flow of energy and materials through the deep ocean, carbon sequestration, so as those skeletons accrue on the seafloor, a lot of carbon is being stored there, and there's also significant amounts of carbon flowing through these ecosystems, through the organisms. Cold water coral can serve as important nursery grounds for fisheries, and who knows what sort of genetic resources may be down there in terms of pharmaceuticals and undiscovered things. As of now, also over 1,300 species associated with water coral reefs. So this includes a bunch of commercially important fish. So they're really own biodiversity hotspots on the seafloor. And as far as threats to cold water coral ecosystems, there's a couple of different suites of threats affecting them that are interrelated. So we have warming, deoxygenation, ocean acidification, and changes in major current systems. So the food supply that is coming from the surface water is going to change as currents change with the climate. And then there's the sort of resource extraction side of this. And it's important to note that these two suites of stressors are interrelated and exacerbate one another. So it's important when you think of deep sea corals from a management perspective that we have tools to locate and protect these habitats before we do any sort of resource extraction. So I'll go through a couple of different threats to corals really briefly. So warming and deoxygenation, as Dr. Clayton said, they often occur together. And this is sort of a bad feedback for corals because the warming increases the metabolic demand for the corals, so they need more oxygen. But at the same time, oxygen is decreasing. And so this can lead to a loss of metabolically viable habitat. This plot on the left here just shows that the oxygen consumption by corals in experimental treatment really differs depending on the temperature. So they really, as it gets warmer in the ocean, corals find it harder to breathe. And this is further made worse by the fact that oxygen is declining as well. And to add on top of that, a lot of corals already live near their thermal and lower oxygen limits. And so we can expect to see their distribution shift towards the poles or deeper in the ocean where it might be a little bit cooler and might be a little bit more oxygenated. And another big threat to corals that is occurring at the same time is ocean acidification. So this is the decline in pH and the saturation of the minerals that these corals need to form their skeletons. So aragonite, which is the mineral used to form the skeleton of Lophelia, when omega aragonite here is above 1, it really favors the growth of these corals. And then when it, as acidification occurs and that value dips below 1, it favors dissolution. And this leads to a decrease in the structural integrity and the health of the ecosystem. So not only is the living coral stressed out for this, it affects their metabolism, it's harder to grow, it's harder to calcify their skeletons, but it actually leads to increased erosion of the dead skeleton that they're growing on top of. And this can lead to a sort of what these authors have termed coral porosis, where these ecosystems sort of crumble as acidification occurs, and this leads to a loss in the really nice three-dimensional habitat where the associated species like to live, and it leads to a sort of more flattened habitat that is not as amenable for species to live in. So moving into some of the work that I'm doing, this is the region where I've been working for the last couple of years. So I'm just trying to answer some really basic questions here. So where is their coral? Where is there not? And because the deep sea is such a vast area, we obviously can't go to everywhere on the seafloor, and it's really cost prohibitive as well. So we need tools to be able to predict where corals are and maybe get at some higher level questions, including how much coral they may be, what are the drivers of their distribution, so are they most affected by temperature, oxygen, how do those things interrelate, and looking to the future, what areas are more likely to be climate refugia. So the area I work in off the East Coast here, as we know, is a really dynamic area affected by this Gulf Stream, which is shown in the plot on the left. And some sites are more near the center or the main axis of the Gulf Stream, so they're being affected by that warm water coming up from Florida, and some areas a little bit more eastward. And so there might be a sort of geography of climate change risk. And one other thing I want to mention is that there's been a bunch of new discoveries in the last few years in this region since 2018. So this Richardson Reef Complex was discovered in 2018. It's about 200 kilometers of continuous cold water coral reef. And then there's a lot of these isolated mounds off to the side and some ridges up here. So a ton of coral habitat has been discovered sort of east of the main axis of the Gulf Stream. And so my thought was that potentially there's a geography of climate change risk in the US where those shallower sites that are closer to the main axis of the Gulf Stream might be subject to some higher temperature and more variation, whereas these deeper eastward sites that have been discovered in the last few years, so those are the ones circled in blue on the right, could potentially be climate refugia because they occur about 800 meters and deeper and a little bit east of the main axis of the Gulf Stream. So what I do is I build habitat suitability models that looks at not only the climate, but it also includes where the suitable terrain is. So we take this multi-beam bathymetry, basically ships go around and send sonar beams down and map the seafloor in high resolution. I incorporate that and climate into these models using all of the known presences of and then build habitat suitability models to predict where on this margin we might find suitable habitat for corals. So I'll start with the terrain suitability. This is the region that has been mapped thus far. This is the compilation of all the symmetry It's mapped at 35 meter resolution, so high enough resolution to really pick out some of these small scale features. As you can see here is the Midland Mounds region, which is off of Florida, where there are tons of these coral mounds. And so using this bathymetry compilation, we can also derive some more variables that describe the terrain in a way that we can predict corals as well. So we can look at the slope of the seafloor, we can look at the aspect of the seafloor, which basically is which direction the seafloor is facing. So whether you're facing into a major current or not. And then there's this BPI, which is the bathymetric position index. And what that is basically is how high a given point is relative to its surroundings. So on the top of a coral mound, it would be a high BPI because the areas surrounding it are lower in elevation, whereas in some of the depressions you see here, you would have a low BPI value because the areas surrounding it are elevation. So using those habitat suitability models, so basically it's just a statistical model that correlates where we find corals to what the environment there is like. We look at how Lophelia has responded to the terrain, and there were three main variables that we could use to predict Lophelia. So they like depth above 1,000 meters, which sort of corresponds with what we already know about Lophelia. They like high slopes, so that influences the currents. So high slopes tend to deliver more food to the ecosystem, therefore encouraging growth of corals, and high bathymetric position indexes as well, which also, again, influence the currents as they flow over the topography of the seafloor. These elevated areas tend to really favor the growth of corals. And so you take these response curves and then use them to predict out in space where suitable terrain may be. You can see there's a lot of suitable terrain in this area. So I've highlighted a few of the most interesting ones. Panel B here is the Richardson Reef Complex, and as you can see, there is a lot of suitable terrain in that area. And we've done about 7 or 8 dives on the Richardson Reef Complex and found that it really, what our models are predicting really corresponds with what we find down there, in that where we're predicting there to be real suitable habitat for coral, we've been successful so far. And then some other interesting sites. Panel D here shows it's as zoomed in, but you can see there's a lot of smaller areas lighting up here. There's in the southern part of panel D here is the Million Mounds region, where there are a lot of coral mounds and a bunch of ridges as well that are favorable for coral. And then panel C and E are these two sites that were mapped in 2018, and there's been one dive executed on each of them, on a coral mound on each of them, where there was really thriving cold water coral populations. So a few years ago, the Blake Plateau was thought to be a little bit featureless, and that, but these recent mapping expeditions have really revealed a dynamic environment where there's lots of coral mounds that we still don't know the extent of. So you can see in panel C here that we have where the mapping sort of ends, there's still areas lighting up. So we don't really know the full extent yet of these coral mounds. So that's a sort of exciting prospect of the future. And it's worth mentioning that these two areas are outside of the coral habitat area of particular concern, which protects these areas from bottom contact fisheries. So there's potential to expand that coral habitat in the future to cover some of these ecosystems that we're just describing. And I just wanted to point out here, this is a map I made that shows the mound density, just to illustrate how many mounds there are in some of these regions. This is the Central Plateau mounds here. You can see in a 2.5 square kilometer region, we can get up to 14 coral mounds. And again, we've only dove on one little coral mound on the very western part of this region. So there's a lot to be discovered about this region, including just how many of these mounds there are as we continue mapping. Okay, now I'm going to move a little bit more into the climate side of it. A lot of this was spurred on by some work that we did with Telmo Morado and published in Global Change Biology that predicted, it made a habitat suitability model for the North Atlantic at a little bit coarser resolution than what I'm working with, but it predicted that there will be temperature-driven losses of Lophelia in the North Atlantic, and that only 1.5 to about 14% of the current distribution will remain suitable. So these would be refugia, and that none of these refugia will be on the southeast US margin. But as I said, we've made a number of discoveries since the data for this paper was gathered. So that includes a few dives on that Richardson Reef complex and both of those plateau mound sites. So these deeper offshore sites could potentially be less affected by temperature changes. And also this paper didn't include high resolution terrain data and was only in the worst case scenario. So in terms of climate scenarios, this was a business as usual scenario. Say we do nothing to curb emissions. This is sort of what we can expect to be the outcome. So my questions were, could there be refugia in other scenarios? And when will we start to see these effects coming on? So I gathered some data from a bunch of global climate models from the newest round of climate model intercomparison projects that includes some more high resolution climate models. So from the high resolution model intercomparison project, gathered data from these models that goes back to 1850 to 2100. And we have a range of scenarios instead of just the business as usual or worst case scenario. So some of you may be familiar with how they used to name these scenarios in the climate model intercomparison project with these RCPs. They've switched to shared socioeconomic pathways that also include some socioeconomic factors as well. So I'll just talk a little bit about the four scenarios I've modeled here. So there's a sort of sustainable future scenario, which is SSP 126, two sort of more middle of the road scenarios, SSP 245 and 370, and then finally a sort of worst case or business as usual scenario where we continue with fossil fuel development, we don't hit the Paris Climate Agreement targets, and business as usual goes on. So I gathered data from these models for seafloor data for temperature, pH, oxygen, and POC flux, which you can think of as just the amount of carbon being delivered to the seafloor. And as you can see here, the Morato paper that modeled the whole of the North Atlantic really used climate model data from the last assessment round that had an average resolution of about 1 degree. So every pixel in the climate model was about 1 degree of latitude and longitude. Whereas in this round where I'm using CMM IP6 and high-res MIP data, the resolution of the data is about 4-fold better in some areas. So throughout the whole North Atlantic, I constructed a model to reconstruct the niche of Lophelia. So basically how it responds to how Lophelia responds to temperature, how Lophelia responds to oxygen, pH, and carbon flux to the seafloor in a multivariate sense. And so constructed the niche for Lophelia and then projected it onto a finite climate grid for the Southeast US in all of those scenarios that I mentioned. So on the left here, you can see just overlaying on the pH map is just all of the different Lophelia points from the North Atlantic used to reconstruct the niche of Lophelia. And on the right here, you can see just a sort of time series of oxygen. You can see this 11.4 temperature band move eastward a little bit. And you can see that a lot of the temperature changes are confined to this shelf area and the near shelf area where a lot of Lophelia occurs. But the temperature temperature increases a little bit further east on the Blake Plateau, might not be as bad. And so this is, again, just the data for the current environment. So that's 1950 through 2014 averaged together. And the white points are Lophelia. And so you can see a lot of, like I said, a lot of the Lophelia points are occurring right on this shelf break where temperature exchanges are predicted to be the most extreme. And you can see that when you look at this data projected into each of these scenarios. So this is what 2100 will look like in each of these scenarios. You can see the temperature increases, which are shown here in red. So the warmer the color, the greater the temperature increase. They're really confined to where the Gulf Stream will be. So it's right over the shelf break primarily. So it's that main axis of the Gulf Stream that is going to get warmer. And that is also, the Gulf Stream effects are also shown in the export carbon data. So you can see that the amount of carbon being delivered to the seafloor is going to get lesser in areas in blue. And so that is also primarily under the Gulf Stream. So those areas that are close to the shelf break that are holding Lophelia may be more affected by some of these climate factors. Oxygen, this far down on the seafloor, there aren't predicted to be really significant changes in oxygen, and these areas are actually pretty well oxygenated now. We didn't find in any of our dives down there any areas that were close to being hypoxic, really. So these corals may be lucky in the fact that they're experiencing less oxygen changes. pH, again, the majority of pH changes are closer to the shelf break, with some of them occurring on some gyres that come off the Gulf Stream, also being a little bit lower in pH. So this is the same data extracted from these plots on the right. These plots show the same data, but for 2100 at each of these Lophelia sites, and then it shows it in each scenario. And so the black line shows the lower limit of pH and the upper limit of temperature in the southeast now. And you can see that many of these sites are going to experience temperatures that are higher than anything being experienced now. And 15 degrees is sort of, in experimental work, that has been shown a lot to be sort of the upper limit, the upper thermal limit to Lophelia. So a lot of these shallower sites near the shelf break are going to be exposed to temperatures above that, and the pH declines, again, are going to go well beyond what is currently in the southeast U.S., although there are corals in the sort of northeast Atlantic that are at 7.8 range now. And this is that same data except in time series fashion. So each of the scenarios going from the best case on the left to the worst case at a couple of the coral sites on the southeast U.S. And so what I just wanted to point out is, especially in this rightmost panel in SSP 585, you see these lines that start at the top at Cape Lookout and Savannah Banks, two of the shallower sites. They actually have some of the highest pHs now, but the rate of change is going to be so great there that by 2050 about, they will sort of pass the deeper sites that are experiencing less rapid changes in pH. Also worth noting that in the best case scenario, this leftmost panel, that pH changes sort of even out by the end of the century. So the pH declines are slowed because emissions are slowed in this scenario. So these are the climate response curves from the modeling I did. You can sort of estimate the relative importance of each of the variables with this modeling too. I'm not going to get too into the nitty gritty of the sort of modeling details. If anyone's interested in that, please feel free to contact me afterwards. I'd love to talk about it. But pH and temperature were the two variables that jumped out as being the most important. Oxygen, as sort of I stated earlier, isn't projected to change too much, and also isn't that variable in the different environments. We found it pretty well oxygenated, so it wasn't as important. As far as the temperature ranges, Lophelia responded well to temperatures about 14.8 degrees. Below that, you see a really steep decline. So we don't find really any Lophelia at temperatures higher than that, and they don't like pHs less than 7.9. And these are just two common model diagnostics that assess how well your model is performing. They both look pretty good, so that we can sort of trust some of these results a little bit with some caveats. But this is then these climate curves projected into space. So we can see in the current environment, pretty much all of the Blake Plateau in the southeast U.S. is currently suitable. So this is the climate suitability index. Almost the entirety of the area is really suitable now as far as the climate goes. So it's a matter of just having suitable terrain as well. But this is not the case in the future. So again, as we go from left to right, the scenarios get worse in terms of emissions. And you can really see by 2100, there are some different patterns regionally going on, especially if you look at it in this sense, where you look at just the change in climatic suitability. You can see that the biggest changes, so the darkest purples, are sort of occurring near the shelf break at these sort of shallower areas, whereas east on the Blake Plateau, the changes might not be as bad. And this, again, you can see as well a little bit more clearly in the plot on the left that shows the climate suitability at all of these sites in each of the scenarios. And you can see this depth refugia effect, where the declines are greater at shallower depths. They're really more pronounced in the higher emission scenarios. So if we go to a sustainable future scenario, there really isn't a huge depth effect. So all the depths will have a sort of moderate decline in suitability. Whereas if we go to the SSP 585 scenario, there's a real disparity between these deeper sites and some of the shallower sites. Again, I extended some of these models to predict the abundance, coral cover of Lophelia throughout the margin as well. So basically just using the habitat suitability and comparing it to the amount of cover at a bunch of segments of video taken from over 20 dives that have been executed on the seafloor in this area, and then predicted the abundance versus what we observe in nature. So about 55% of the variation in abundance that we see can be predicted in this sense. And when you project that into space, you can see these plots aren't the most clear, but you can see that some of the areas that are lighting up in the colors are areas that have pretty high cover of Lophelia, or predicted to, and that in the future there are much less of these areas. So a lot of the western Blake Plateau goes from being suitable to really predicted to only have like remnant populations of really low cover of Lophelia left. One exception to that is this Richardson Reef complex over in the right, where you see some blue areas lighting up. Okay, just to summarize that a little bit, Lophelia is widespread and really abundant on the southeast U.S. margin, especially more so on the Blake Plateau than we previously appreciated just a few years ago. And so getting this high resolution terrain data is really important for making fine scale predictions. So as more mapping data comes in, I'm sure we'll continue to make new discoveries and learn a lot of more. So it's a really exciting prospect for the future. And another thing that came out is that we learned that climate change refugia may exist on the Blake Plateau, but it really is dependent on the scenarios, first off, and some more info that we need on coral biology. So this sort of modeling work needs to go into them with more, lab work, including genetic variability, how plastic are the responses to temperature and pH, et cetera, how fast can Lophelia evolve, how fast can it acclimate, and the scope of change is really dependent on the mission scenario, but also how variable the environment is. So these models were built on sort of the long-term change in temperature, but by putting landers on the seafloor, you can see that these environments are really variable on smaller timescales as well. So this is lander data. So we put down a lander as part of the Deep Search project. So it's a sort of project with BOEM and USGS. We're going to a bunch of these sites throughout the southeast U.S. And exploring them. You can see that there are temperature changes that go up to about 6 degrees on the scale of days. And there are sort of food delivery fluxes that come at the same time. So these are the short-term temperature pulses that are basically surface water being delivered down to the reef. So a sort of short-term surface water downflux that might have to do with the Gulf Stream meandering over the site. And so if the sort of modeling work that I presented needs to be compounded with experimental work that incorporates these sort of short-term changes. Because long-term changes, these sort of spikes that are happening tolerable now, but as temperature increases, those spikes may pass well over some known thermal limits. This to region. Am I over time here?
We're getting pretty tight here.
Okay,
yeah,
I'll wrap up.
Great, because we do have some questions.
So the deep sea coral data portal. So this is from NOAA. As you can see, the presences of stony corals sort of thin out in the mid-Atlantic, where you don't have sort of areas where coral can grew over time. Of stony corals really continue well up here, and there's a lot of really dense soft coral gardens on the New England Seamounts.
Did we lose your audio, Ryan?
Okay, can you hear me now?
Yes.
I got disconnected from audio. Okay, so just to wrap this up, most of the corals that exist in the mid-Atlantic are confined to the canyons where you have vertical habitat. And so you don't get the sort of large stony coral reefs that you get in the southeast US because the corals that occur on the vertical habitat, they can't accrue over generations. And these canyons and seamounts aren't really well resolved in climate models. And so a lot more work needs to be done to sort of figure out whether these areas might be refugia, but they are really biodiverse areas, including presences of both tough corals, so some hard corals, some isolated Lophelia colonies, and a lot of really nice soft coral communities that have high biodiversity as well. So there's still a lot to learn. We haven't been to most of these sites where there's predicted to be coral, so there's a lot of ground truthing of these models in conjunction with experimental work that I mentioned, where we need to incorporate some realistic environmental conditions. So stony corals are likely to at least be diminished somewhat by climate change, and this leaves sort of area for other species such as soft corals and things that don't build skeletons to potentially expand. Sponges might take some of the ecological niche that are left behind by stony corals. But all this depends on the magnitude and how emissions are changed in the future. Okay, thanks everyone. And I'd like to thank everyone associated with this work. This did not happen in isolation. So lots of people helped in the Deep Search project and at Temple University and out at sea where we gathered a lot of this data. If we have time, I'd love to take any questions.
We do have a question, and I'll ask Carol Ann to turn her camera on too. But I think this one is for you, Ryan. What was the paper that showed Lophelia forming reefs and Lophelia forming more flat, less rugose habitat? I don't know if that's a paper link that you could provide. I'm
not sure exactly what the question is asking.
It just says, yeah, I don't know if you can see it in the question box too, but a paper that showed Lophelia forming reefs and Lophelia forming more flat, less rugose, less rough.
Okay. Sure, that is Hennig, I'm not sure the pronunciation, Hennig et al. In Frontiers in Marine Science. It's a paper, it has coral porosis in the title. That's what they termed the effects where declining pH and omega aragonite saturation was really affecting the 3D complexity of these habitats.
Great. That was the only question we had in the chat, and I know we are at 3 o'clock, but I just wondered for each of you what you thought would be the critical next step in your research. And maybe Carol Ann, is it learning more about those bubbles?
I would say that, for both weather, which we didn't talk about in climate research, really understanding the lowest layer of the atmosphere and the uppermost layer of the ocean and how those connect to each other from physical, biogeochemical ways is really key. And we need it at very high resolution local places to get the physical processes right for the models. And then we also need it globally. So on a proposal for a new NASA satellite, we'll see if it gets funded, but it's again to look at things globally. So both directions.
Yep. Thank you. And Ryan, how about you? I know you were focusing more on the southeast, but of course we're really worried about the mid-Atlantic. Do you think the mid-Atlantic corals are going to be as vulnerable as those southeast ones?
I forgot, I didn't really mention it, but a lot of these corals, like I said, are occurring in canyons, but those are environments where food supply is generally pretty high. So that might be able to buffer a little bit of the climate change effect. So there's been some work showing that corals are able to cope with low pHs and low oxygen in a couple of areas where food supply is really high. So potentially that might buffer some of these effects a little bit, but my answer to what we need to do sort of goes in line with what Carol Ann was saying, in that we need higher resolution models that can really resolve some of the stuff going on in the canyons. There's been some work putting down landers in the canyons as well, so we get an idea of what what the environment is like on a sort of week to monthly time scale. So I think that's really important for resolving some of that as well.
Great. Well, thank you both. I wish we had more time. We just, Lizzie Duncan says, thank you very much. Great talk. So thanks for joining us, Lizzie. And again, we will be sending all the attendees an email with a link to the recording from the webinar. And we're also going to be asking you what you'd like to hear about next in this series about corals and canyons. We're trying to put one together on marine debris impacts on corals. So if anybody knows anyone working on that, let us know. And that might be our next one if we can pull it together. We're trying to get Tim Shank over there at Woods Hole. And I think it's so exciting. I believe the Oceanus Explorer is in the Hudson Canyon today. I think Kevin Hassel was on the call with us just now and got an email from him. So I know NOAA's trying to get out there and make more of this research happen. It is expensive, but it's so important that we get a better understanding of what's happening out there before anything is lost. So I think with that, I just want to thank you both again so much for putting these talks together for us. And we really appreciate your time and all of your good work. And thank you very much. And again, thanks to Gordon and Betty Moore Foundation for their funding to Marco to help us make all these things happen. So with that, I'll wish everyone a good day. Take care.